We've already looked at similarity as it applies to 2D shapes and one-dimensional lines, mainly using triangles, quadrilaterals, that sort of thing. And we know that mathematical similarity is the same process as enlargement, okay? If one shape or line is similar to another, then it's an enlargement of another by a scale factor. Now, that isn't just true of a single line, okay? In one dimension, it's also true of a shape in 2 dimensions and a volume in 3 dimensions. And that's why we call this dimensionality. Okay, so as an example, to explain what's going on, let's consider something nice and simple. Okay, so let's consider a cube of 1 by 1 by 1. We'll just use a standard unit, okay? And then let's consider an enlargement, a mathematically similar shape, or a solid, I should say, seeing as it's 3-dimensional. That is this one. And we're going to say that it has been 2, 2, 2. Okay, so we have an enlargement by a scale factor here, so timesing by a scale factor, and we have an enlargement here, which is dividing by a scale factor, or we could say it's timesing by the reciprocal of the scale factor, which is the same thing. Okay, so going this way, we say it's small to big, or S to B, and this one we say is big to small, or B to S. Okay, now let's consider a bit more. Okay, so let's consider how the dimensions are connected. So length, and we'll have small here, and we'll have the big one here. So length, we have 1, and the big one, each of the sides is now 2. Okay, now let's consider area, or in this case, surface area. Okay, so the surface area of the small one, so it's each face is 1 by 1, which is 1 unit squared. There are 6 of them, so this is 6 units squared. Okay, other one, we have a face that's 2 by 2, which is 4, and there are 6 of them, so 4 by 6 is 24 units squared. Let's look at the volume. Volume, 1 by 1 by 1, 1 unit cubed. Here, volume, 2 times 2 times 2 is 8 units cubed. Okay, now let's look at the mapping more, the scale factors, if you like. So, to go from 1 to 2, we have multiplied by 2 to go that way, okay, small to big. To go from 6 to 24, well, we've multiplied by 4. Okay, and to go small to big in volume, we've multiplied by 8. Okay, to go the other way, we have divided by 2, or times by its reciprocal, which is a half. This way, we've times by a quarter, and this way, we've times by an eighth. Okay, now, each one of them is a different scale factor, okay, which is something you probably might not have expected, but then we have to apply dimensionality to this, okay? So, if we think about length, length is 1 dimension. So the scale factor is 2, but in a single dimension, it's 2 to the power 1. Surface area is 2 dimensions. 4 is 2 to the power 2. Volume is cubic. 8 is 2 to the power 3. So there you can see where the scale factors in the different dimensions come from. And we can summarize that by saying if this is the linear or line 1 dimension scale factor, okay, which is a linear scale factor 1 to the power 1, this is the area scale factor, okay, which is the ASF, and that is the linear scale factor squared. This is the volume scale factor, or VSF, and that is the linear scale factor cubed. So what this shows us is that we now have a link or relationship that connects the various scale factors through the dimensions via the linear scale factor. And that's how we work out most of these questions. Here's a classic example of a dimensionality question. Okay, so here we have two bizarre looking shapes. It doesn't matter what shape they are. Okay, so what we know is that they're mathematically similar. So one is an enlargement of the other. Okay, so the one on the left is the big one, so we'll just call it B. And the one on the right is the small one, so we'll just call it S for small. Okay, so it helps us to be able to talk about them. Okay, so what have we got? We've got three numbers and an unknown. Okay, and this is what we're always looking for if we're going to discover the relationship across the dimensions of the enlargement itself. Now, you're always going to get two numbers which are in the same dimension, and it's those that are going to give you the scale factors to start with. Okay, and then you'll probably get another pair in the same dimension, which is a number and an unknown, and that's what you're going to work out. Okay, so let's get started then. So we are looking to go, we're looking for x, which is a linear, and it's paired with this linear. So we're going to have to work out what to times 7 by to get x. So that's going to be a linear scale factor, and it's a small to big one because we're going from the small shape to the big shape, yeah? So linear scale factor, small to big. That's what we're after. Now, what do we have here? We have another pair of two numbers, but these are volumes. So this is a volume scale factor, and it is small to big. Okay, and we know that the relationship between linear scale factor and volume scale factor is cubed, but if we're going from volume scale factor to linear scale factor, it's the inverse of cubed, which is the cubed root. Okay, so that's how we're going to work this question out. So our first thing is we need to work out what the volume scale factor is going from small to big. Okay, and that's nice and easy. Volume scale factor, small to big, is, well, we always put the bigger one on top, don't we? Because we're going to be times by something that's bigger than 1. So that's going to be 91 over 38. And that's a scale factor. Don't worry if it's a horrible fraction, because unless they give you some nice numbers that can easily cancel down and are cubes and squares, you'll be using a calculator. Okay, so that's the linear scale factor, small to big. We want the linear, that's the volume scale factor, sorry. We want the linear scale factor, small to big. And we know that that is the cubed root of the volume scale factor. So we can write it as a root, or if we want to be proper mathematicians, we can write it as an index, okay? It's good practice for your index skills. So you should know that when we have cubed root, the denominator of the fractional index is always the root. So it's the third root is the third power. So that's the same as that to the power of a third, okay? Doesn't matter because you can use either method on the calculator, but it's just good to know that. So there is our linear scale factor, and all we've got to do then is x equals 7 times our linear scale factor, which we now know is 91 over 38 to the third. Stick that in your calculator, and you should get 9.365 centimeters. Don't forget the units, to 3 decimal places. Okay, when you've worked it out, always check to make sure it makes sense. Okay, so we know we're going small to big, so the number has to be bigger, okay, which it is. If it wasn't, we've probably got the fraction the wrong way around. But that's the essence of these questions, okay? Find a pair of numbers in the same dimension to give you the starting scale factor. Then you'll probably have another pair somewhere with one number and an unknown in another dimension. And all you've got to do is work out from the two numbers what that scale factor is in that dimension, the relationship between that dimension and the one you're after, okay? And then once you've gone down to that, multiply that by the value you've got to get the unknown. Here we have a different type of question, no nice diagrams. And whether we want to debate whether those diagrams are nice is up to you. Okay, now we know what we're looking for. First off, do we have two objects, items, solids, anything that are mathematically similar? Well, yes, we do. Okay, so we can tick that, nice and mathematically similar. Do we have a pair of numbers in the same dimension? Well, here we have their heights, so that's linear, that's the same dimension, first dimension. And we have a ratio, okay, so two numbers. Now, normally you're given lengths, so 20 centimeters, 70 centimeters, but they just become a ratio anyway. So as long as you've got two numbers, you're fine. So that's what we need to work out our first scale factor. Now, we need another pair in a different dimension. Well, we have heights here. Well, now we're talking about surface areas. So that's the second dimension. That'll do. Okay, we have one number in that second dimension, and we need to find this one. So there you go. So it's exactly the same question as one before. I've just managed to pull out all the important information. Okay, so let's start then. So we have two shapes, A and B. Now, from the linear, we can see that the ratio of 2 to 7 means that A is the small one, okay, and B is the big one. And they've given us the linear information, okay? So we have linear information is 2 to 7. Now we know that area, whoopsie-daisy, sometimes you get too close. Okay, area is, okay, the linear squared. So we can just square, 2 squared is 4, 7 squared is 49. Okay, so that's the ratio of the surface areas, all right? Now, we're looking to go towards A. So going to A from B is big to small. So we're looking for the area scale factor from big to small. And that is going to be 4 over 49. Okay. Now, if you're stuck on how we got that, we have the ratio of surface areas of 4 to 49. Yeah, but we're going from the big to the small. So if you're going to multiply by a scale factor that's going to make something smaller, it has to be less than 1. So that's how we know the smaller number goes on top. Okay. And then it's nice and simple. Here is the surface area of B. We want surface area of A. So we times it by 4 over 49. Okay. And that gives us 3.51 centimeters squared to 2 decimal places. Okay, so essentially dimensionality is find the first scale factor in whichever dimension you can, and then it's just a case of manipulating it by going up and down the dimensions. Okay, so say they gave you a volume and you wanted a surface area. You'd take the volume scale factor, you'd cube root it to go down to the linear scale factor, and then you'd square that to go up to the area scale factor. Okay, hope that's been useful. Bye-bye.